In this part of the course, I will introduce you to Monte Carlo simulations. This is very powerful and at the same time relatively easy tool that allows us to solve very complex problems. But before we get to Monte Carlo simulations, we have to talk a bit about loops in R. Yeah? Loops are a programming structure that allows us to repeat certain tasks many times, and we decide how many times. The most popular loop in R is for loop. Yeah, and the structure of this is that if we write for and the block of the code that we want to repeat, and in the for loop, as an argument of for loop, we provide so-called iterator, a variable which changes in every loop of the operation, and then we provide an object over which we iterate. Yeah, and in most cases this is some sequential vectors of elements. Yeah, and here if we write something like this, and here we write print I, then in every loop our I will take the value of the very first element, and then after executing the first loop, it will move to the very subsequent element of this object until the very end. Yeah, and so here we're printing all elements of a sequential vector from 1 to 10. R is quite flexible regarding the object over which we iterate. Yeah, so in particular, it doesn't have to be a vector, numerical vector, but it can be any vector. So for instance, element 1, element 2, element 3. And here, if instead of from 1 to 10, instead of this vector, we provide this, it will work just fine. Yeah, it is worth mentioning this because it's not a common thing for all programming languages. In R or in Python, yeah, this works this way, yeah, and from time to time it's quite useful. And here we have another example. Yeah, we can, for instance, generate 12 random variables from uniform distribution. We can obtain this with function runif. Before I mentioned function rnorm, which was for normal distribution. For generating random numbers from uniform distribution, we use runif. Yeah, and we provide a number of elements that we want to sample. And now we can use exvec as an argument in our for loop. Yeah, and this is it. And if we want to print those elements, we can use, and here j is equal to j. Function paste creates a string out of many elements, yeah, that we provide. So if we write something like this, and also numeric, some numeric values, it will, as a result, we will get one string that can be provided in print function. Yeah, so here the purpose of this function is to iterate over generated vector from random variables. Yeah, and yeah, those are numbers that we sampled. This is the first loop structure, and the second loop structure is so-called while loop. For loop is a very convenient programming structure, but in this type of loops we have to, in most cases, we have to know how many iterations we're going to do. Yeah, and however, there are some problems where simply we don't know. And one of problems of this type is as follows. Yeah, that suppose that we want to keep drawing random numbers from normal distribution as long as we draw positive numbers. And after the first time of drawing negative number, we want to terminate our loop. Yeah? So in this problem, basically we don't know how many iterations we're going to need. Yeah, and so for loop, it would be very difficult to generate such a snippet of code. Yeah, and but for while, it's not a big problem. Yeah, because here we want to keep xsim. We draw our first element, and it can be positive, it can be negative. Here it's positive, and we keep drawing as long as we keep repeating this loop, as long as this condition inside while is true. Yeah, so here in our case it will be this print xsim here end of the while loop and print xsim once again. Yeah, and okay, we print xsim and we draw new value. Yeah, and depending whether this xsim is positive or negative, we repeat this loop. Yeah, so here. Yeah, it's in the first row we generated negative number, so this loop wasn't run. Yeah, if we run this once again, still we are not lucky. We are not lucky. Again and again. Okay, here. Yeah, yeah, it was weird. Yeah, here we draw positive number. Yeah, and we kept drawing positive. We kept drawing numbers from normal distribution until we draw negative number, and then we skip this loop. Yeah. So okay, here also. Yeah, there are a few cases. Yeah, and. Yeah, so this is while loop. Now we know what are loops, and actually at this moment we are in the position to introduce the Monte Carlo methods. Monte Carlo methods is a set of tools developed by, the idea was developed by Stanisław Ulam, a Polish mathematician from University of Wisconsin-Madison, during the project Manhattan. Yeah, the project Manhattan was this project in which American scientists tried to produce first nuclear weapon for American government. Yeah, and this whole process involved a lot of very complicated mathematical problems, yeah, and some of those problems were super hard to solve, yeah. And Stanisław Ulam proposed a method that can, by using simulations, the solution to those problems can be approximated using computers. Yeah, and in our class we will discuss about three applications, but we will use two methods. Yeah, so let's start with the most intuitive illustrative example. First, let's analyze the problem that we know how to solve it analytically, and let's write a function that computes the area of points enclosed by a circle of radius r. Yeah, so first here Monte Carlo, methods, and analytical solution. And so we can create function circle area that as an argument it takes r radius, and the formula for the area, yeah, from elementary school all of us know that it should be pi times r to the power of 2. Yeah, it works super easy. Yeah. So now we wrote a function that computes an area inside a circle, and in this function luckily we are equipped with closed form formula for this area. Yeah, and now let's do it. Let's try to compute the same thing but using those so-called Monte Carlo simulations. Yeah, and before we move forward, we will need one library which is not included in base R, Plottrix. And now we can load this package simply by typing library Plottrix. There are several commands in this package, but we're interested in function draw a circle that as arguments takes the center of a circle and the radius. Yeah, so if we type this here, we will get something that we don't like. Draw circle is low-level graphic functions, so this put our circle on the existing plot. Yeah, and now what we would like to have is to create new empty plot where we can put our circle. How to create an empty plot? We can do it this way. Plot, just to type some coordinates of one point, then we provide limits of our plot, just like here, -1, let's say. Okay, let's put it here, -2. Okay, yeah, and if we type this, yeah, we will get not exactly what we would like to have, because here we have this one tiny point in 0, 0. Yeah. So now what we can do with this is just to plot this once again, but we can use function type, which tells R whether we want to draw point or line or nothing. Yeah? If we write type n stands for nothing, and let's put x lab x, y lab equal to y, yeah, and now we have empty plot. Now, when we have an empty plot, we can use our function. Yeah, and while this may look that this is what we would like to obtain, it's not. Because notice that those two extreme points should touch a vertical line at -1 and 1. So let's do it. Vertical -1 and 1. Here everything is fine, but if we plot horizontal lines, we will see that there is some space, and this space comes from the fact that if we use plot without additional options, then the length of unit on x-axis and on y-axis don't have to be equal. Yeah, and to make this point equal exactly to this point, we have to set our aspect ratio. Yeah, and here by providing this, there is option ASP. We set it to 1, and if we plot it here, and now this is exactly what we wanted to obtain. Now in this figure we have, amongst others, two shapes. Yeah? One is circle, that we would like to compute the area inside the circle, and square with side of length here from -1 to 1, here from 1 to 1, so this is square with side of length 2. Yeah, and suppose that we know how to compute the area of the square, but we don't know how to, what's the mathematical formula, PR square, to compute this area. Yeah, and here we will use Monte Carlo for the first time. The area of this circle using simulations can be computed in this way, yeah, that we can draw lots of points randomly that are placed inside the square, and then we have to count how many points are inside of our circle. Yeah, and then the percentage of our points inside the circle times the area of the square will be approximated area of the circle. Yeah. So first let's create a small number of random points, 100, and we should draw from a uniform distribution that the probability of each point inside this square is exactly the same. Yes, so let's create this, and here we use function runiv. We provide the number of points that we want to draw, and also if we are able to provide min and max. If we don't provide this, everything is drawn from uniform distribution with min equal to 0 and max equal to 1. but in our application we want to draw points from interval -1, 1. Yeah, so we type -1, max equal to 1, and we do exactly the same thing for coordinates coordinates on y-axis of those points. Yeah, using this. Yeah, the very last object that we create is whether our points are inside. Yeah, and we can generate numeric vector of the same length as that row of inside vector corresponds to points xy sim, yy sim. Yeah. So right now, inside are all our zeros. Here and here we have drawn points that we can add to our plot. We can add those points to our plot by using low-level graphic function points xy. Sorry, not xsim, ysim. Okay. You see, all points here are drawn from this from our square. Yeah, and now what we will have to do is to count how many points are inside this R, and if those points are inside this R, this square, then we have to change the element for this point from 0 to 1. How to check whether our points are inside the circle? In this exercise we will use this mathematical formula. Yeah, and yeah, so we don't know the formula for the area of points inside of points inside the square, the circle, but yeah, we will use. But this formula is known by us. Yeah, and so now we have to check. We have to iterate over all elements, over all points, and if xsim I, so we iterate over subsequent elements of xsim I plus ysim I to the power of 2 is smaller or equal to, here we are interested in circle of radius 1. Yeah, so here we type 1, and if this is true, then we should change the value of the element inside I from 0 to 1. Yeah. Let's run this loop. Okay, and now we have a vector with 0 and 1s, where 1 corresponds to those points that are inside of our circle. Yeah, and if we want to compute what's the fraction of those points to all points, we can type this. This sum inside, this counts all those elements with that have value equal to 1, and divide over length of this vector. Yeah, so here we see that 80% of those points are inside of our circle. Yeah, and now if we want to compute what's the area, what's the approximated area of the circle, we need to multiply this 80% by the area of our square. Yeah, and in our case it will be the area of this is 2 times 2 is 4. Yeah. So the approximated area of this circle using Monte Carlo simulation with only 100 elements is equal to 3.2. Notice that it's not the exact the same what we have from analytical solution, yeah, but here we simulated only we made the simulation only with 100 points. In this exercise we can avoid using loops, yeah, and actually this is highly recommended to, if you can avoid using loops in R, it's better to avoid it, because R is still, in comparison to other programming languages, it's terribly slow. Yeah, while for instance Fortran and Julia it's super fast with loops, Python and MATLAB so R is the slowest. Yeah, so here we will translate this loop to loopless structure, and to this end we will use if-else. Yeah, if-else takes the vector of conditions as the first argument, and then depending whether this condition of in a given row is true or false, it changes this element to one of those two options. Yes, so here we can use this, but without here we provide vectors of conditions. Yeah, and if we type something like this, we'll have, yeah, a vector of true and false values that tell us for which elements this condition is met. Yeah, so this is it, and now we need only to change is that if this is true, then we provide value equal to 1. If it is false, this is 0. And if you type this way, yeah, we will get exactly, yeah, the code will work exactly the same way. Yeah, but instead of using loop, here we used if-else statement. Yeah, and now we may be not very satisfied with the quality of our approximation. Yeah, and to increase this, we can change this to, instead of 100, we can draw 10,000 points. Yeah, and you see we're getting closer and closer to the true analytical solution. Yeah, let's check whether this will be computed quite. Yeah, this is yeah, this is 100,000. Yeah, 1 million. We can type this or this way using scientific notation. Yeah, 14, 15. There should be 29, 92, 90, 93. Okay, yeah, I forgot. 90. Yeah. Yeah. So you see, we see that if we draw more and more numbers, then our approximation is better in is closer and closer to our analytical solution. Yeah, so obviously when we have some closed form formulas, it's better to use closed form formulas, but for some more sophisticated shapes, we may have no such closed form formulas. A useful plotting exercise will be to plot all not 1 million points, but let's first reduce this to 100 points, and let's create this. We have a vector that indicates whether some point is inside of the circle, yeah, and if we want to plot those points, let me reset this plot. Yeah. This and here also this, yeah, and we have our points x sim y sim. We can do it, we can plot, and yeah, we have our points. But now, if we want to, we can use a vector inside to change the color of our points. Color equal to, and now we will use again if else. If inside is equal to 1, then the color is my favorite one. If it's outside, it will be here. Yeah. You see, here all those points are inside. We can play around with this even more, because also we can change style of our points. So if we type, now I don't remember by heart names for different styles, but we can use numbers. Let's say 1 and 2. PCH accounts for style of plotted points. Here we have this, and hopefully we will get different color. Yeah, we see. Yeah, so this is it. And also, it's only with 100 points. If on the other hand, repeat this with much more points, let's say 10,000, be less and less visible. Okay, something is wrong here. Okay. I think that I should now hopefully. Okay. Previously I forgot, so I initialized inside, but I forgot to run this this function, which is key for us. And now if we run this once again, then we will get, yeah, and then get this what I wanted since the very beginning. Yeah, and so here, yeah, we see that there are more and more points. Yeah, the figure is less and less. It's more difficult to read this. Yeah, but that's the illustration of Monte Carlo method. Yeah, of the first application.